in this lesson, we're going to get some more practice simplifying trig expressions. So we learned about all those different fundamental identities that we were using in the last video to simplify them down. We're going to continue to use those, but now we're going to add a couple problems where there's some factoring involved. Okay, so it's going to be helpful to just review these two factoring problems before we get started with those. So take a second, pause the video, see if you can identify the answers for these, what would these factor to, and then unpause the video when you're ready. So this trinomial looks a little bit different than we're used to seeing a trinomial. Typically we see a trinomial where the leading term is x squared, right? We have x squared, and then this would be minus 5x minus 14. So we're more used to seeing something like this. So how then would we factor this where it's to the power of 4 and this is squared, okay? Actually, it's not going to be altogether too different from how we would factor this trinomial, okay? So if we were going to factor this trinomial in blue, it would break apart into two binomials where both of them begin with x, and then we think of two numbers that multiply to make negative 14, so 2 and 7, and they add to make negative 5. So that would mean that the 7 would have to be negative, and the 2 would have to be positive for them to add to make negative 5. So it's still going to be the same as that, okay? So if we're doing this to the power of 4 and to the power of 2, it's still going to be the same thing. The only difference is that our x that we have here and here is going to be squared. That is it, okay? So that's the only other thing that we have to add. We just make sure that those are both x squared, but it's still plus 2 and minus 7, and that would be our answer. The next problem, hopefully you recognize this as difference of squares, okay? So it's a binomial, and they're both perfect squares, so if I were to take the square root of both of them, excluding the negative that's between them, this would also break apart into two binomials, both beginning with x. So the answer for this first term, when we take the square root of x squared, we just get x and x, and then the square root of 121 is 11. So I put 11 and 11, and if you remember how to do difference of squares, one binomial is positive, the other is negative. Great. So after that quick review, now let's look at some more problems, okay, where we have to simplify these trig expressions. So we're going to use factoring to simplify these first two problems. Again, I would encourage you to pause the video, see if you can come up with the answer yourself, and then you can get started. So for this first problem, what I'm noticing right away is that I have two terms, and so I need to clearly identify what both of those terms are. So this right here, this whole entire thing, that is one term. This is a second term, okay? So if I'm going to use factoring here, think about something like this, almost like you would think about x, like the x represents secant squared, so x times y, and the y is the tangent squared x. So I have secant times tangent plus another secant squared, okay? So if I look at something like this, how would I factor something that looks like this? Well, if I look at those two terms, and this is one of those, one of the first things you have to look for when you're factoring, is there a greatest common factor? Is there something that both of these terms have in common? So that would be secant squared x. Both of these terms have a secant squared x. So what I can do is remove that as my GCF. So I'm going to divide both of these terms by secant squared x, okay? Because I'm taking that out as my GCF. So secant squared x, that's my GCF. What happens when I divide that from this first term? Well, it cancels here, and all I'm left with is tangent squared x. What happens here? What am I going to get when I do secant squared x divided by secant squared x? Okay, well, hopefully you see that this simplifies to positive 1. So anything over itself just turns to 1. All right, so now we're left here. After we've factored out a secant squared from both of those two terms, we have this left over. And then, because I see that this is tangent squared, okay, tangent squared, my attention is drawn over here to my Pythagorean identities. So I see here that tangent squared, whatever that angle is, plus 1, we can take that and rewrite it as secant squared. So I'm going to take this whole thing here and rewrite that as secant squared x, okay? And then that is being multiplied by this other secant squared x that was the GCF, okay? So I have both of those multiplied together. What is that now going to give me if I multiply the two of these, okay? Well, think about it like this. If I had x squared times x squared, what does that give me? I would add the exponent, so I get x to the power of 4, okay? So here, my answer is going to be secant to the power of 4, okay? So secant x to the power of 4. All right, let's try out the next problem. This one might be a little tricky if you don't end up rearranging some of the terms, okay? So I'm going to arrange them in descending order. So I'll put cosine to the power of 4x as my first term. So I'm actually going to draw boxes around these terms so we can clearly distinguish them, okay? So you can see exactly what I'm doing. So that's my first term, that's one of my terms, this is another term, and then this one here would actually be another term as well. So I have 3 separate terms here. I'm going to leave this negative 2 cosine squared x in the middle because I'm writing this in descending order, and then I'll put the 1 at the very end, and this is going to be a positive 1, so I'll write this as plus 1. So now that I've rearranged this, hopefully you can kind of see that I would be doing a problem that's fairly similar to the one that we had for the bell work, okay? I would be doing something like this. So it's a little weird because we have the cosines in there. So one thing that I do suggest is actually to remove the trig function that you have in there for just a moment so you can see what it looks like without the trig function. So if I didn't have cosine in here, what would this look like? Well, this would be x to the 4th minus 2x squared plus 1. So that's a little bit of an easier problem to look at. So let's actually try factoring this, and then at the end, we'll put the cosines back in, okay? Sometimes I find that's a little bit more helpful is if we can remove part of that weird part, and then we can add it back in later, okay? So if we were to factor something like this, this is going to factor into x squared, because this is to the power 4, and then I'm going to have minus 1, minus 1. So those two numbers multiply to make a positive 1, they add to make negative 2. Great, so that's what this will factor into, and then now I can go ahead and add the cosines back in, okay? So I'm going to rewrite this as cosine squared x minus 1 and cosine squared x minus 1, right? Great, so now I've factored this. Is there anything I can do now to simplify this even further? So hopefully you recognize that since this is a trig function that's squared, I'm probably going to lean on the Pythagorean identities, okay? Specifically the one at the top here. So I'm actually going to write that up here. So I have sine squared x plus cosine squared x equals 1. How can I rewrite this or manipulate this so that it looks like cosine squared x minus 1? So what I could do is I could subtract 1 from both sides. So then I have sine squared x plus cosine squared x minus 1. That canceled, so that makes 0. So I just move that 1 over to the other side. So now I see that cosine squared x minus 1 there. I just need to get this sine squared moved over to the other side, and then I have what I want. So if I subtract sine squared from both sides, now I can clearly see that because this is going to cancel, I can clearly see that cosine squared x minus 1 is equal to, I can replace that with sine squared, or negative sine squared x. Okay, so I'm going to take this binomial and replace that with negative sine, or negative squared, can't talk right now, negative sine squared x. So I replace that with negative sine squared x. I'm going to do the same thing with the second binomial. I'm going to replace that with negative sine squared x. Okay. So now that I have this, it's kind of like the problem we had a minute ago. These two terms are being multiplied, so when I multiply them together, I'm going to add their exponents, okay? And then since they're both negative, a negative times a negative makes a positive, so this should be written as sine to the power of 4, and it is positive. For these last two problems, we're now going to practice verifying this identity. So if you remember from this last video, the right side, we're not going to touch, so don't touch this at all. And then the left side, this is what we need to manipulate or change so that it ends up looking like what we have on the right. Okay, so I need to change all of this so it ends up looking like 2 secant squared theta. Okay. So what I'm going to try to do, since this is already in terms of sine, is let's make these denominators the same so that I can add these two fractions together. Okay, so I'm going to rewrite this right now in red. So I'll put 1 over 1 minus sine of theta plus 1 over 1 plus sine of theta. So just rewriting that. And this is very similar to a problem that we did in one of the earlier videos, but we're going to multiply both sides by a fancy 1 so that we can make the denominators the same. So I'm going to multiply this side by 1 plus, so I'm using the denominator from here, so 1 plus sine of theta over 1 plus sine of theta. So this is just a 1, and then this fraction I'll multiply by 1 minus sine of theta all over 1 minus sine of theta. So when I do this, I should get the same denominator so I can add these together. So if I'm multiplying straight across, the numerator here should be 1 plus sine of theta. When I multiply the denominator here, I'm going to end up foiling because I have two binomials. So if I were to FOIL all of this out, a little shortcut to this is since both of these look exactly the same, the only difference is that one is negative and the other one is positive. And let me put a plus sign there so it's clear to see. So since the only difference is that one's positive and one is negative, when we multiply these, when we FOIL them, the middle two terms are going to cancel out, okay? So this is going to happen because these are difference of squares, okay? These are factors of difference of squares. So my result should just be those first two terms squared, so 1, and then the second two terms squared, so positive and negative sine squared. So this is going to end up being negative sine squared. So basically I just take those two, multiply those together, and that's what I would get once I FOIL. You can do that and see that once you end up FOILing all of this, the two middle terms would cancel and I would be left with this as my denominator. Okay? So now that I have that, if I multiply the right-hand side, I get 1 minus sine of theta, same denominator, 1 minus sine squared of theta. So now that we have the same denominator, we can go ahead and add both of these fractions together. So 1 minus sine squared theta in the denominator, and then in the numerator, 1 plus 1 is going to make 2, okay? And then the signs are going to cancel when I add those together, okay? So all that's left in the numerator is just 2, okay? And then in the denominator, I recognize that this is probably going to lead me to a Pythagorean identity, okay? So if I were to just simply subtract sine squared from both sides, okay? So subtract sine squared from there, subtract it here so it cancels. 1 minus sine squared of theta, I could rewrite that as cosine squared. So I'm going to take this and replace it with cosine squared theta. And 2 is over all of that. And I'm really close to proving this identity. All I have to do now is actually use one of the rules from before, which says that if I have 1 over cosine theta, another way that I can write that, or that is going to be equal to secant. Okay, so this was one of the fundamental identities from before. I can write 1 over cosine as secant. So translating that to this problem, even though there's a 2 in the numerator, that's totally fine. I can still use this rule, and even though this is squared, I can still use this rule. So I kind of tend to think about it like this. If I want to take cosine and move it up to the numerator, it has to change to secant. Okay, so I kind of think about taking this in slow motion, moving it up to the numerator, and it has to change into secant. Okay, so this is going to be written as 2 secant squared theta. Okay, and that's exactly what I want to see. I've verified this identity. It's good to go. All right, and then the very last identity we have to verify. Again, don't touch this part on the right-hand side. You can start off by trying to change this in terms of sine and cosine, but what you might end up finding out is that once you do that, it's going to be a little tricky to actually get to this place that you want to get. Okay, so I'm going to show you another strategy that you can use to more quickly get to verifying this identity. Okay, so what I'm going to try to do right now is this 1 plus cosecant. Okay, if only this was squared, then we could use it in a Pythagorean identity. So my goal right now is I want to rewrite this. I'm going to change this so that if it is squared, then I can use a Pythagorean identity. So how could I do that? Is there a way I can manipulate this so this would end up being 1 plus cosecant squared? So I could, if I multiply this by a fancy 1, kind of like I did with the last problem. So if I multiply this by 1 minus cosecant over 1 minus cosecant of theta, when I do this, I'm going to get in the numerator, and I'm actually not going to distribute these. I'm going to leave these separate. So I'll just do 1 minus cosecant theta. That'll stay in parentheses. I don't want to distribute that with cotangent squared theta. And you'll see why in a second, why I'm not distributing those. But then in the denominator, this is going to be like the last problem. This is going to turn into 1 minus cosecant squared theta. So that's what you would get if you end up foiling these two out. The middle two terms would cancel because one is positive and one is negative, and they look exactly the same other than that. Okay. So now this is in a spot where I can use a Pythagorean identity finally in the denominator. All right. So if I was to take this bottom identity, how could I rewrite this so it looks like 1 minus cosecant squared theta? So let's say I subtract cosecant squared theta over to the left-hand side, so I get 1 minus cosecant squared theta. And then if I subtract cotangent squared theta, so I subtract cotangent over to the other side. So basically those two flip-flop around. This moves over here, this moves over to the right, and I have to subtract both of them to move them over. So now I know that 1 minus cosecant squared theta, I can replace that, all of this, I can replace that with negative cotangent squared theta. So this right here, it's replaced with negative cotangent squared theta. And the numerator still looks the same. So now by replacing this with negative cotangent squared theta, this is going to allow me to actually cancel this cotangent squared theta out. So can cross this out here. And then this negative is going to be represented still as a -1. So that'll still be in the denominator as the negative. So I'll have the -1 in the denominator. And then I'll have that over 1 minus cosecant of theta. We're super close to our answer now. The one last thing that we can do to get to our final answer is I'm going to take this -1 and I can actually split this up between both of the terms in the numerator, okay? So I can take this -1 and I can put it underneath the +1 there. And then I can take the negative cosecant and put it underneath the negative cosecant. So I can split that up between those two terms in the numerator, so then that will allow me to simplify this to -1 and positive cosecant theta, which is exactly what we see here. The two terms are just flipped around, so I still have positive cosecant and -1. You can switch it around if you want to, but it's still the same thing. So that would be verified.